It's me, Mario!
Super Mario 64. It's one of the most important and beloved video games ever made. It set the standard for 3D games at a critical phase in the industry, not just influencing titles on the Nintendo 64, but subsequent releases on many a competing platform. But how did it actually work? Is there anything interesting happening in the minds of the Goombas, Koopas, and other enemies we find idling around Bob-omb Mountain, Whomp's Fortress, and Tick-Tock Clock? Well, let's find out. Now you might think, oh come on Tommy, Mario 64 is like super old, and the AI isn't that great in that game. But it's important to recognise what this game represents. It's a pivotal point in the history of game development. Mario 64 was the top-selling title of the Nintendo 64, and during a time when game development was migrating to 3D. It had a huge influence on how three-dimensional games were designed. While it wasn't the first 3D platformer, a credit owned by PlayStation title Jumping Flash, nor is it even the first 3D title made by Nintendo, Mario 64's legacy cannot be understated, with developers such as Tim Schafer and Michael John outright stating the huge influence it had on projects of their own, such as Psychonauts and Spyro the Dragon respectively. While areas such as camera controls would merit further iteration, aspects of visual design, character animation, player movement, level and mission construction set the template for many other games to follow. But what about the AI? Sure, it's going to be rudimentary, but is there anything interesting we could glean from it? Ideas of how to structure and design behaviour? Surely this might be useful to know, especially for game devs trying to do something of their own. All it would take is for one idiot to dig through the code to find that out. And my friends, I stand before you as a professional idiot with time to spare. To make this happen, I downloaded the Mario 64 decompilation hosted on GitHub. This project was first published back in 2019, and is just one of a number of works from a community of hobbyist decompilers who take it upon themselves to reverse engineer the raw binary of the ROM file into parsable, legible code in the C programming language. So what I'm covering in this episode is based not on the actual original sourced by Nintendo themselves, but the reverse engineered code that is publicly accessible and designed to be as close to the original as possible. That said, the original source code did make its way onto the internet during the infamous Nintendo Giga Leak back in the summer of 2020. Given the rather sketchy legal territory that could put me in, I opted not to base this episode on that leaked source code. I wanted to make sure that anyone who is curious can explore the details in this episode safely by checking out the decompilation project. That said, I did find a copy of the original source code by digging into some dark and damp corners of the internet. Ugh. And from what I read, the differences between the original source and the decompilation are largely negligible for the purposes of my research, making this community effort all the more impressive. This decompilation isn't driven by a desire to steal Mario assets, make new ports of the game, or enable handsome Scottish professional idiots to make videos about it, but rather, in the case of Mario 64 anyway, it was a mechanism to help speedrunners find new exploits. For many of the developers involved, being able to piece together the puzzle, one function at a time, is the real reward. Decompiling source code like this isn't an easy task at the best of times, but it's made all the more difficult by having to figure out just what development tools were being used when the game was built back in 1996. To decompile a game like this one, you need to have an idea of which version of the Silicon Graphics IDEO compiler was used to generate the ROM file, and testing all of this requires emulating the system behaviour of the original Silicon Graphics development units, the SGI Visual Workstation, given this is what would have been used by developers building games for the Nintendo 64. It's a real feat of engineering, and something that, as a programmer myself, I'm in awe of, quite frankly. If you want to learn more about this work, including the efforts to decompile the likes of The Legend of Zelda Ocarina of Time, check out the Ars Technica article linked to in the video description. The decompiled source code, once properly configured, allows you to compile the ROM file for each regional version of the final game, Japan, US and Europe. However, in order to create a fully playable game, you still need a copy of the original game ROM, given this project only contains community-written source code. it doesn't have any of the in-game assets. Otherwise, big old Ninty would start swinging the banhammer. The situation is slightly similar to that seen with the official release of source code alongside Command & Conquer Remastered, given that too didn't have the art assets either, meaning you can't just compile it and boom, free copy of the game. Don't forget, I already made a video digging into that project as well, so be sure to check that one out if you haven't already. Ultimately, what this does mean is that modders, hobbyists, and, well, anyone with the time and inclination could create modified versions of the game once they figure out the inner workings. A good example of this is the PC executable of Mario 64 that was floating around the web in 2020, followed by even more fan ports to the Nintendo 3DS, PlayStation 2, PS Vita, Dreamcast, and even Android phones. Plus, mod tools can now be built that will enable easier world editing and asset replacement. So, enough of the background, let's get into it. Is that pretty much every single element in the world outside of the level geometry is considered a behaviour attached to it as well. Behaviours enable for a variety of common functions, be it to spawn in an object at the location such as a coin, make the object fall as a result of an interaction, customise the hitbox for collisions between in-game objects, turn to face the camera when prompted, disable the render because it's destroyed, and much more. Behaviour scripts are not exclusive to AI characters. Moving platforms, doors, coins, fireballs, shockwaves, and even some trees and butterflies are considered to have behaviours, given they all respond to the game world in some form or another as a result of interactions or the passing of time. But all objects that carry behaviour scripts have two main functions, their begin function and their update function. These do two very specific things. Begin is responsible for configuring this object for the game now that it has spawned in, while Update handles the behaviour of the object for each tick or frame of the game. Mario 64 typically ran at around 30 frames per second, with some of the most intense parts of the game running at around 20. So while Begin is only called the first frame the object exists, Update is called every frame afterwards. If you're a game developer yourself, then this will all sound very familiar to you, given the likes of Unity and Unreal have a very similar structure. The update function handled the execution of common behaviour commands for each object type, unit movement along the X and Z axis, as well as on the Y axis compensating for gravity. Plus it pays attention to all the logic for managing timers for actions, whether the object had switched from one action to another, all of which I'll come back to in a minute, but the most important thing, given it's literally the first bit of computation each object does, is it checks where Mario is relative to it. The first two calculations of each object with the behaviour script is to figure out the distance from Mario and the angle required to turn and face him. This is used for a variety of AI features which we'll see shortly, but it's also used critically for the rendering of in-game objects. It's important for games to have smooth performance, and one common way to minimise overhead for the GPU is a process known as occlusion culling. This helps maintain performance of the game by only rendering objects the players will be able to see, but also you may render objects at varying levels of quality, based on how far away they are from the player, a practice called level of detailing or LODing. The Nintendo 64 was the first console to implement a Z buffer, a portion of memory in the hardware to ensure the occluded polygons are not being rendered. While this is a common feature in modern graphics cards and consoles, it had to be implemented at a software level for the likes of the PlayStation and Sega Saturn, the latter of which was generally terrible for building 3D games on, given the hardware wasn't really built for it. However, this didn't mean the developers relied on it entirely to ensure smooth performance. Every behaviour-driven object in Mario 64 decides based on its proximity to Mario whether it should even bother to render or not. Each has their own drawing distance parameter, and every frame it checks to see if Mario is now farther away than the draw distance, at which point it tells the renderer for that object to disable itself. Interestingly, I couldn't find evidence to suggest that the behaviours don't execute when Mario is too far away, but certainly it stops drawing them to the screen. The one exception to this is if an object is in a room. Mario levels are built either as an open space, such as Bob-omb Battlefield, or they're comprised of multiple rooms. The three notable examples of this are of course Peach's Castle, but also Big Boo's Haunt and Hazy Mae's Cave. In these instances, the object will only render when Mario is in the same room, and in fact, a lot of behaviour scripts are also only activated when Mario is in that room as well. Now, outside of the main behaviour functions, an object would also carry a pointer to a separate behaviour command script. These scripts are written for more bespoke elements of the game, and allow for the execution of the bulk of the game's interactions and behavioural logic, There are over 500 of these in the game, and range from everything like specific non-player character behaviours to the triggering of red coin collections, activating traps, even ending the level by collecting the power star. And that's where we find some of the more fun AI facts, so let's dig into these a little more. Like the main behaviour script, the separate behaviour actions used by NPCs have their own begin and update functions, and I'm going to walk through some of the more interesting stuff that I found. As mentioned already, all game objects compute their distance and angle relative to Mario for rendering, but also many of the NPCs use this for their core logic. Those who have played the game will have noticed this, given the likes of Koopas and Goombas react to Mario's presence. But on top of this, many of them record their home. This is a location in the game world that is often stored in their begin function, meaning they store a reference to where they spawned into the map or very close to it. This is used so the NPC knows roughly where in the world it appeared when the level loaded in. It's worth mentioning that NPCs in Mario 64 can't compute on the likes of a navigation mesh to figure out how to move around the world, because, well, there isn't one. And what we now consider a nav mesh in game engines didn't exist until Quake 3 Arena in 1999, a point I covered in my AI 101 episode on the subject. Even in my video on GoldenEye we discussed how they had to build a custom system to allow guards to move from one room to the next. Instead, for Mario, NPCs such as the Goomba and Koopa Troopa will simply wander around on the available terrain with fixed rules on how far they go before changing distance and often rotating in fixed angles. You'll note that they stay on the surface they started on the majority of the time, and a lot of Mario 64's levels aren't filled with clutter, meaning it's harder for them to get stuck behind obstacles. There's only a handful of enemies that will ever move across platforms, but that's largely due to dumb luck from jumping, rather than anything happening at a code level. But as they move around, they often pay attention to two things. The first is whether they're going to collide with walls, in which case they will turn away from them. But how does it know it's facing a wall? There are functions that allow for them to resolve collisions based on their current heading, and often there's some wriggle room there. The same applies for when they are looking at Mario, given it's not based on their exact heading, because that's maybe too precise, but whether Mario is within some range of their heading, which effectively means every non-player character in Mario 64 is blind, they're simply reacting to Mario being roughly in front of them. The second key fact they focus on is how far away from home they are. Each NPC has different rules on how far away from home they're allowed to go, and whether it's the total distance from home, which is the logic used by a Goomba and Koopa, or if the distance on a specific axis has been reached, which is used by Bob-omb, or in the case of Boo, whether it falls within a radius of their origin, calculated using their X and Z movement. In any case, the general rule is that they will turn around, face towards home, and start wandering back in that direction. But in some cases, notably Bob-omb and the Bully, they only return back to home if it's deemed safe, which is determined by whether Mario is currently in proximity of their home location. And it's this logic that encapsulates most AI characters, but they all have their own unique caveats. Goombas make hard turns away from walls and double back to home if their total distance is too far away, but they will then chase Mario if he's too close, regardless of angle, at around 500 units, with chases always preempted by a jump. Now wait, hang on, distance units? Let me explain. Mario is approximately 161 units tall in the game, and given he is, according to the Mario Wiki, 155 centimeters tall, that's close enough to consider near equivalent. So when we say within 500 units for the Goomba, it's just shy of 5 meters. Meanwhile, Koopa Troopas have a similar logic, albeit they run away from Mario within 300 units. The interesting part in the Koopa logic is that once you jump on them, they can lose their shell. In general, they will try to run back to their shell, but quite often Mario is too close and will force them to run away. However, if the shell is close enough, despite where Mario is, it will take the gamble and try to dive back into its shell. As mentioned, Bob-omb's patrol based on how far away on any axis they've travelled from their home, although to be fair it's difficult for them to ever go anywhere of distance without subsequently blowing themselves up. But unlike enemies such as Goombas, when a Bob-omb dies, it triggers a respawner in the code that will create a brand new Bob-omb where the last one appeared after Mario has safely left the home area. Meanwhile, other enemies like Whomps check their distance from home and compare that against a predefined patrol distance. This is then configured on a per level basis. In the case of Whomp, it has the same patrol distance for all levels with exception of Bowser in the Sky, which is much shorter. Heave-hoes that appear in Tick-Tock Clock and Wet Dry World also exploit the home and Mario locations, but in a slightly different way. In this case, the heave-ho records its home location on start, but once Mario gets within a certain range of home, it then starts homing in on his exact location. Now, I can't possibly make a video about Mario 64 and not talk about the fish. As we know, fish AI is a very important aspect of any game and what really helps sell the top quality experience players have come to expect. Fish spawn in two variations, blue and cyan, plus the schools of fish that spawn in come in two variations, the large school of 20 fish and the smaller school of 5 fish. Fish, when spawned in, start with different starting speeds, given a little bit of random noise is added. Plus their height in the water is also varied to make sure they're not all clumped too close together. The fish themselves have a pretty simple set of behaviour. They dive and ascend, turn fixed angles with some random noise as well, and then they make sure they turn back. Their height is typically capped such that they can't get too close to the water surface, with a strong negative vertical speed applied if they get too close. The one exception to this is the secret aquarium, because there is no water surface in that level. To make sure they don't wade too far away from home, fish can only move within a fixed range of around 700 units, but also the school usually spawns somewhere between 1500 and 2000 units of Mario being in the map. But, and this is the super intelligent AI behaviour for you, all fish will react to Mario being in the water. When Mario is less than 150 units away, they turn to be pointed away from Mario, and all of them will then speed up, setting a standard that the games industry would continue to follow for many years to come. And now, because I couldn't think of any other way to group all this knowledge together, let's bring back another AI in games favourite. Ladies and gentlemen, and variations thereupon, it's time for the speed round! First up, just about all 3D objects are stored within graph nodes, and each node often has multiple child nodes. Mario himself is comprised of multiple nodes, which makes it easier to achieve functionality in specific sub-areas, like turning his head and scaling his hands and feet larger during attacks. On that note, Klepto the Vulture never actually steals Mario's hat. The game just disables the renderer on the graph node for Mario's hat, and Klepto magically produces a new one in his claws. The cheeky b****. Each object in the game has a variety of physics parameters. This includes the hitbox radius, gravity, bounciness, drag strength, friction and buoyancy, and these can all be edited in code. Plus the physics is influenced by their physical scale, hence in Tiny Huge Island, the Goombas are using the same physics, but it's respecting their overall change in size. Each NPC has a variety of attack handlers, allowing for the game to more specifically customise how a given enemy will react to Mario hurting them in different ways. Sounds slightly cruel actually. Bob-ombs have a fuse timer of 150 time units, but the explosion code cannot execute until Mario has successfully dropped them. What does that mean? Well, it means they can blow up when you're holding them, but if you decide to throw them, they have to wait until they hit the ground, which is really considerate of them. Boos actually oscillate up and down when hit, but it isn't scaled correctly, meaning their vertical velocity goes from 1 to -1 and back to 1 over 32 frames of play. This means in practice, it's a really small change, only around 5 units of vertical movement. As such, it's almost unnoticeable for the average player, until now. The Racing Penguin in Cool Cool Mountain not only stores the logic for checking whether or not you cheated in the sliding race, but also stores it for future reference. Clever girl. All the Koopa logic is stored in the same file for a regular Koopa, a tiny Koopa that only appears on Tiny Huge Island, and for Koopa the Quick, a special character who appears in several Power Star challenges. The same applies for the Wumps, with all the logic for regular Wumps and the Wump King in the one file, and the Boos and King Boo. But King Bob-omb gets his own file. I wonder what makes him so special. Lakitu always aims to throw a spiny in front of your current heading, so zigzagging is really important right there. The haunted items in Big Boo's haunt, such as the bookshelves and the piano, also use AI code but are relying on the room logic, only activating provided Mario is in the same location as they are. The bouncy bubbles fired out the water cannon actually calculate their own bounciness and how many times they've bounced. They're very clever bubbles. Big Boo actively pays attention to how many little Boos you've killed in combat when fighting him in Big Boo's haunt, which is really sad when you think about it. But it's fine, they're ghosts, they're dead already, I guess. There's a variable in the code that, depending on how you interact with an object, has a different meaning. If you destroy it, the variable tells the game what the coin value of the object was. However, if the object hurts you, the same variable is used to figure out how much damage you take. When you enter the room of the castle for Jolly Roger Bay, there's a bunch of fish in several aquaria. They don't use the same AI code as the rest of the fish. There's a custom behaviour script just for these blue fish chilling in the tank. Oh, and there's always 15 fish in each tank every time. Heck, even the birds that appear in the ending of the game have their own separate behaviour script too. There's unfinished code that suggests that the fishing Boo enemy from Super Mario World could have made an appearance, in which it would have used fire circles that would slow Mario down if he was caught in proximity of them. And lastly, given this is such an old game, the blinking of specific characters isn't handled by an animation, it's all done programmatically. Mario, Yoshi, Peach, Bowser and several other NPCs manually blink, often by hot swapping a texture used on a part of their 3D model. In fact, many have unique variables for how long it's been since they last blinked, and whether their eyes are open or closed. The weird part is that Mario and Bowser still blink even when the game is paused. Most NPCs' blink logic is actually triggered by a random number generator, but that logic can't be called when the game is paused. However, Mario and Bowser blink on what is known as global time, which means that logic continues to run even when you've paused the game. And there we have it, the special 64th episode of AI in Games on Super Mario 64 is coming to a close. I couldn't possibly cover any other game for this one, especially because I received so much flack for releasing the Hitman video as episode 45. I know, it still hurts. Still, go watch that video, it's still pretty good, I think. This is of course not the first time we've travelled all the way back to the Nintendo 64 era, with episode 44 of AI in Games checking out the inner workings of the AI of GoldenEye 007, with assistance from none other than the great Dr. Doak himself. Plus, if you enjoy these episodes where I crack open the source code, be sure to check out the aforementioned episode 53, where I looked at Command & Conquer, plus the AI 101 episodes on finite state machines and goal-oriented action planning, where I looked at the codebase of Half-Life and Fear. AI in Games is a crowdfunded series, and it's these good people right here that help make it a reality. Without them, you wouldn't get more videos and listen to my lovely voice. To support my work, get early access and more, check out the links on screen and in the description. Be sure to share it, be sure to like it, be sure to subscribe it, or I'm gonna come round your house. Nah, I'm kidding, like, you all take care of yourselves and I'll be back.